welcome to Zenomatics. This is your video for daily dose of mathematics. In this video, we're going to do a really tricky question from integration, A-levels paper 3. This question creates a lot of trouble for a lot of students. I will first show you the question right on the screen in the beginning. So have a look at this question, be terrified by it, give it a try, and then let's try to solve this question. So all three parts of these questions have created a lot of trouble for many students over the past few years, and let's crack it down in this video. So let's begin. I'll start with the first question, first part. It's integration by substitution, basically. So let me start with the main equation, first of all. So this is, we have to take the substitution u is tan x. And we are going to try to integrate from limits of 0 to 1/4 pi of tan of n plus 2 x plus tan of n x dx, and we have to show that it will go to 1 over n plus 1. So this is the integral that we have to show. So first of all, as we are used to the idea that whenever we are given a substitution, so first of all you have to differentiate your substitution. So this will be du by dx, and this would give us secant squared x. And once you cross multiply and make dx subject, it would be du upon secant squared x. So I've made x as subject, and that is du over secant squared x. So let's start to place this over at that position, and we will be able to see what happens next. Now, so for integral, I'm going to ignore limits for a second so that we are able to. So this is tan of n plus 2 power x plus, so first of all, I should start getting rid of tan by writing it as, so this is tan of n plus 2, so I'd be okay writing u raised to power n plus 2, and plus this would be tan x to the power of n. So this would be u raised to the power of n, and over on the outer side we will have du over secant square x. Secant square x. So what I have done over till this part is that I have substituted tan x with u at both places, and for dx I have made a substitution of du over secant square x. It's not completely successful substitution as of now, because we have u and x still present, and first of all I'm going to try to get rid of this x, and the way we're going to do that is through this identity that we have been learning in paper 3. 1 plus tan squared x is secant squared x. It's a very important identity that you must know in paper 3. Then we use it, at 3-4 places, and you must know that secant square and tan are very closely related. So let's apply 1 plus tan square at that position, and we'll be able to see it would be u raised to power n plus 2 plus u raised to power n over, this thing will become 1 plus tan square. Secant square will become 1 plus tan square, and instead of writing 1 plus tan squared, I'm going to choose to write 1 plus u squared. And this is the final equation that we have. Now, what we're going to do is we're going to take u raised to power n plus 2, and I'm going to break it as u raised to power n and u squared. It would be u squared plus u raised to power n upon 1 plus u squared du. Let's take u raised to power n common over here. So if I take u raised to power n common, it would be 1 plus u squared over 1 plus u squared. Here onwards, things are going to simplify a lot. So if I take this fraction and do some simplification, we'll get rid of these two terms, and we are left with a very simple integration, which is u raised to power n du. And if we can see, we can take power as an operator because box would be u and differentiation of box would be 1. So condition is fulfilled. The integration would be u raised to power n plus 1 over n plus 1. So this is the integral for this. Now let's address the limits. So there were two limits, one was 0, one was pi by 4. So I'm going to make a box for change of limits over at this side. So for limits, if I take lower limit as x is equals to 0, and I put u is equals to tan x, so this would be u is equals to tan of 0, and we know tan of 0 is 0. And second value is x was pi by 4, and for u is equals to tan pi by 4, we know pi by 4 is 45, so tan 45 would be equal to 1. So two limits for u will be 0 and 1. So let's bring those limits in our final integral and put both of these limits as 0 and 1. Let's apply the upper limit first. So it would be u raised to power, I had to place the limit at for u. So it would be 1 raised to power n plus 1 over n plus 1 and minus 0 raised to power n plus 1 over n plus 1. So we know that question will it solve currently.
A few moments later, 2,000 years later.
Okay, so this would be 1 over n plus 1. 1 raised to power anything would be 1. So this would be 1 over n plus 1 and minus 0 raised to power anything would be 0. So this would be 0 over n plus 1. This would go away. And we will have our final answer as 1 over n plus 1. This is what had to be shown. So this was a basic question. Basic idea was to apply integration by substitution. We had to make a substitution. We had to make another substitution at this point. Once we were done, there was a little bit of simplification involved. This part was a little bit tricky to identify that for u raised to power n plus 2, you can write u raised to power n and u square separately, then take u raised to power n common, and you're left with 1 plus u square. So this was a bit of deep thinking that you have to do for this part. I'll just erase this node and make another part, and then continue with the second part. So now we have done the first part. Let's move on to the second part. I'll display the second part on the screen as well for you so that you can see what we have to show. We have this result from the first part, and the second question requires to find the exact value, and the word used is hence. Hence, we have to use the result from the first part. We have to find the exact value of this expression that you're looking at the screen. I'll write it down over here as well. So from 0 till pi by 4, we have to integrate secant to the power 4x minus secant squared x dx. Because it is a connected question with part 1, it's a good idea to first think of this part and think of bringing it in terms of tan. And again, the identity that we're going to use is 1 plus tan squared is secant squared. So I'm going to get rid of secant square terms and I'm going to go towards tan. Before that, I would like to take secant square common. I'm ignoring the limits for a while because we know that we can put the limits back again once we are in a relevant form. So I would take secant square common. This would look like this: secant squared x times secant squared x minus 1. Okay, so this secant squared can be written as 1 plus tan squared. So I would write 1 plus tan squared for the first secant square. And for secant square x minus 1, if you look closely, if this 1 goes to the other side, this would become secant square x minus 1. This would be equivalent to tan square x. So this second bracket would become tan squared x. And if I multiply this tan square inside, I will have two terms: tan squared x plus tan to the power 4th x. Now the first thing that we have achieved till here is that I have brought this entire expression from secant square in terms of tan. I'm going to switch the terms places and I'm going to show you how it is going to relate with the result from the first part. So I'm going to write it the other way around. So it would be integral of tan to the power of 4 x plus tan squared x dx. I'm going to stop here for a second and I want you guys to evaluate, can you see the resemblance between this expression and the expression from part A? The resemblance that you would see will be the value of n. We can clearly see that the value of n is 2 over here, and this would be n plus 2, so this is actually 2 plus 2. So where 2 was n. So indirectly, this part is telling us the value for n. The value of n that is placed over here is 2. So in this expression, if I put 2 over here, this part will become 2 plus 2, that would become 4. So I know that this expression is same as this expression from the first part if I take value of n is equals to 2. Now I know that the final integral of the first expression is 1 over n plus 1. The answer would be same for this one as well. So it would be 1 over n plus 1, and we have decided that the value of n is 2. The final answer would be 1 over 2 plus 1, and hence this integral would be equal to 1 over 3. I'm going to go over this idea once more so that you guys are comfortable. I started off with secant square terms, and because I had to relate to the first part, that part was in tan terms. I applied this identity, brought all the secant square terms in terms of tan, and once we were there, we started to see the resemblance between the first part and this expression that we had. We clearly saw that the power n was equal to 2. And this second expression helped us a little bit with that. So when n was equals to 2, this n plus 2 would be equal to 4. So now we know that this expression is equivalent to the expression from the first part if we put n is equals to 2. So all we had to do, we had to go to the final answer and put n is equals to 2, and this would give us the final answer. Before I move on to the next part of this question, which is the trickiest part of this question, I'm going to just pause for a second and erase the entire board so that we can start again. Okay guys, so basically this is the last part of this question, and this is by far honestly the most counterintuitive part that I've ever seen in an A-levels exam. So I would just give you like a second to have a look at this, and then I'll just show you the solution. That how the trick was how to relate this part, this expression, to whatever was given in the first part. So in the first part, we can see we have to have two terms of tan, one with a power n, and the second power would be 2 more than that. And this is the pattern that we have to follow. And if we follow that, the final answer would be 1 over n plus 1. Now we have 4 terms over here in front of us, and we have to bring them to this pattern. I'm going to warn you guys beforehand, this is counterintuitive, and I do not assume many of the students to look at it and be able to solve this right away. So let's have a look at this. This is a tricky scenario. So I want my expression to be a pair of tan values with their powers are differing by 2. So one power would be n and the other power would be 2 more than that. And we can see there is some similarity. We have 9, we have 7, we have 5, we have 3. We have powers with a difference of 2. So we are somewhere nearby, but not exactly. These 5s are a bit distracting because as we can see, there are no coefficients behind tan terms in the first expression, but there is 5 over here. So let me show you the counterintuitive step and then we'll take it from there. So I'm going to break it down like this. It will be tan to the power of 9x plus. For 5 tan to the power 7, I'm going to break it down into tan to the power 7 plus 4 times tan to the power 7x plus this 5 tan to the power 5x would be broken as 4 times tan to the power 5x plus tan to the power 5x plus tan cubed x dx. All right, so let me show you what has happened in this step so that you guys are not left behind. So 5 tan to the power 7x is broken down into 1 tan plus 4 tan. So this is 1 plus 4, 5 tan to the power 7x. This 5 tan to the power 5x is broken down into 2 terms, 1 tan and 4 tan terms like this. And why have I broken them like this? I'm just going to show you in just 1 second so you guys will see the magic trick. I'm going to pair them in terms of 2 each. So to visualize this better for you people, let me draw. These are the pairs that I'm going to make. And in the second pair, we can see there is a 4 common, so I'm going to take that 4 out. We know we can separate integrals if they are being added or subtracted. So I will have one pair of tan to the power 9x plus tan to the power 7x dx. In the second pair, I'm going to take out this 4 common, and I will be left with tan to the power 7x plus tan to the power 5x. And for the last one, we will have tan to the power 5x plus tan cubed x. All right, now if you have somehow made it this far into the video, it is very rewardful because now you guys can see what is happening over here. We have this pair of tan terms where these 2 powers are differing by 2. So if I take n as 7 in that expression, so if I take n as 7 over here, this must be 7 plus 2, that is 9. So n is 7, where n plus 2 is 9. So if I take n as 7 over here, this would be n plus 2. In this expression, if I take n as 5, my n plus 2 should be 7. We can see this is following the exact same pattern. And for the last term, if I take n as 3, then n plus 2 would be 5. So we know that if this expression follows that pattern, final answer would be 1 over n plus 1. So for the first one, the answer should be 1 over n plus 1. N is 7 over here. So 1 over 7 plus 1 plus 4 times. For this one, this is again following the same pattern. The answer should be 1 over n plus 1. N is 5 over here. So this is 1 over 5 plus 1 plus, for the last one, again 1 over n plus 1, and n is 3 over here. So this would be 1 over 8 plus 4 over 6 plus 1 over 4. And if you add all of them together, I think this gives our final expression, that is 24 upon 25. So I understand this question is a little bit counterintuitive, but not impossible to think. There was a trick involved where you have to separate those terms. And of course, you should not do these questions right in the beginning of the paper. These sorts of parts are usually left behind for the end of the exam, so that you have done everything important and easier and on medium scale of difficulty by the time you are attempting these parts. I would never recommend to engage with such parts in your paper 3 while you are in the first hour of your paper at least, or even first 1.5 hour of the paper. Such parts should be dealt with in last 15 to 20 minutes so that you have nothing else to do. You have covered most of your grade, and now you are free to, divulge yourself into these sorts of difficulties. If you have understood this question, I salute you for bearing this video till so far. And if you liked this, please share it with your friends. If you have any other queries, any discussions that you want to do, you can leave a comment below and I'll try to reply. Thank you so much. I'll see you in the next video. Goodbye.